Hello, everyone, and welcome. My name is Jessica Williams, Programs and Community Partnerships Manager at Chabot Space and Science Center, and we are thrilled to bring you another exciting program live from your homes this evening. Thank you so much for tuning in. Tonight, we have with us aerospace engineer Dr. Lauren Abbott from NASA Ames Research Center to talk about the NASA Mars 2020 mission that just launched yesterday. Dr. Abbott is an aerospace engineer at NASA Ames Research Center in Silicon Valley, California. She uses computational modeling and simulation to investigate and design advanced materials for the extreme environments encountered in space exploration. Some of her recent research has related to thermal protection materials for heat shield technologies used in atmospheric entry, as well as high temperature protective coating materials for advanced space propulsion technologies. She obtained a dual Bachelor of Science degrees in mathematics and physics at the Indiana University of Pennsylvania, followed by a Doctor of Philosophy in Materials Science and Engineering from the Pennsylvania State University. Tonight, she will give an overview of the technologies that enable Perseverance to make the roughly 9-month journey to Mars, starting with the launch on Atlas V541 rocket and ending with the landing of the Perseverance rover on the surface of Mars using the sophisticated entry, descent, and landing system, as well as take a closer look at the thermal protection materials that make up the spacecraft's heat shield, which keep the spacecraft and rover safe during entry into Mars's atmosphere. We will also take questions from the audience at the end of Dr. Abbott's talk, so be sure to post your questions in the chat at the end. Thank you, Dr. Abbott, for joining us.
Great, thanks. Thanks, Jessica, for the great introduction. So I'm Lauren, and I've been at NASA about 3 years now. And one of the things I never really realized until I got to NASA is all the very cool stuff that goes on at NASA. I mean, you hear about some of the, I guess, the greatest and latest applications and missions, but there's a lot that goes on behind the scenes, and of course, a whole lot of people with all sorts of different expertise to make those happen. So one of the things I wanted to talk to you about today are all the cool technologies that we get to develop for space exploration. And in particular, due to these extreme environments that we often find in space exploration, we have to develop new materials to make technologies work. And that's what I do at NASA. I'm a materials scientist and engineer. So I help design these advanced materials that can help us do all these wonderful things that we'd like to do at NASA. So I pulled together some slides that I'm gonna pull up and share real quick. All right. So as I mentioned, I want to talk about some of the advanced materials and technologies that we've been developing, in particular for the Mars 2020 mission. So hopefully some of you got a chance to check out the launch yesterday. But I also wanted to give you an insight into some of the new materials and applications for technologies that we're developing that go beyond Mars 2020. So maybe on the near horizon, as well as some that are maybe a bit further out. So let's get into it. All right, so quickly, just to mention where Ames is. So Chabot is not too far from Ames Research Center. We're just in the heart of Silicon Valley, where we can interact with all sorts of great companies and help us develop all those cool technologies. We're just on the south side of the bay near Mountain View in Moffett Field. So I'm sure many of you, at least the local attendees today, have probably driven by. You maybe have seen our large wind tunnels or the big hangars that are outside at Ames. This is what our campus looks like. And it's just one of the many centers that are at NASA, which I showed on the previous slide. But each center, something you may not know, is that each center has its own specialized areas that they work in. And that's true for Ames. So we have 8 core areas that we research in. That doesn't mean we're restricted to those areas, but those are the areas that we do the most. And today what I'm going to talk about are the 2 on the farthest right side of the screen. So entry systems, as Jessica told you, that's where I work. So I work on the systems that help us enter into a planet's atmosphere that might be returning to Earth, or it might be going to Mars. And I'm also going to talk a little bit about the advanced computing technologies that we have at NASA. So we have a huge supercomputer that's actually hosted right here in California at Ames. And we use that supercomputer to do all sorts of large modeling and simulations to help us support our missions. And that's something I do. So I'm a computational materials scientist. And that means a lot of the work I do is on these large supercomputers, leveraging the power that they provide. All right, so before I get into Mars 2020, I wanted to do a quick overview of some of the past Mars missions that we've had. This is not, of course, all of the missions that we've done, but this is the last 20 years or so. And I have here 2 halves of the screen. So the first on the top, I have orbiters. So these are all the missions that we've sent orbiters to Mars, and these just orbit around Mars and collect data from orbit. They might take pictures, they might take measurements, but they're really focused on just collecting data from orbit. And you can see we've had 3 that have been going for a very long time. All these points on the line here tell you when they launched, and the arrows are indicating just how long they've been in operation. So in fact, many of these can operate for many years. And then on the bottom half of the screen, I have all the landers and rovers. So these actually make it to the surface of Mars, and they'll collect data and take pictures at the Mars surface. And that gives us, of course, a much better understanding of what's going on than just the orbiters can provide alone. One thing I think is important to realize is that when we design these missions at NASA, we're always building upon what we've learned in previous missions, right? So it's not that we want to start from scratch every time we do a new mission. We often use the technologies that we've learned from in previous missions and the data we've learned from previous missions, and we help that in the design process for our new and upcoming missions. And in fact, the Perseverance mission, the Mars 2020 mission, is very similar to the Curiosity rover. The designs are very similar. We've taken advantage of a lot of the work that we did for that mission to make this mission a success. All right, so of course, the star of the Mars 2020 mission is the Perseverance rover. And it's going to do some pretty cool stuff, and maybe you've read up a little bit about it, but where it's going is Jezero Crater. And the reason we've picked Jezero Crater to send the rover is because we think a long time ago, this is maybe where a lake might have existed on Mars. This picture here shows you what looks like a river delta. And we think this is a really good place to start looking for signs of life. And so that really fits into the 4 kind of core objectives of the mission that I have listed here. So we're going to be looking for habitability, right? How habitable could Mars have been a long time ago? This is something that our rovers have been doing for a long time on Mars. But one thing that Perseverance is going to be doing that we haven't really done before is directly looking for signs of life. So we're going to be seeking these biosignatures that could actually tell us that life might have existed a long time ago on Mars. Another thing that's doing this, it's just really super cool and I'm really looking forward to, is it's going to be caching some samples. So that arm that you can see coming out of the front is going to be able to drill into the rock and pick out rock samples, and it's going to collect them into tubes and leave them on the surface of Mars so that we can maybe go and retrieve them in the future in a different mission and bring them back home. So there's a lot of analysis that we can do on Mars, but we can't do everything. So it'd be nice if we can bring those back with us to Earth and really do a full analysis to really understand what's going on and if life might have existed. And then the last thing, like I mentioned, we always build upon our mission. So anytime we go to Mars, we try to do things that we can use to prepare for human missions. That might be learning about the climate of Mars so that we're prepared when we send astronauts in the future. We also test out new technologies that might help us with human missions. So these are all kind of the core areas that we're looking forward to in the Perseverance rover mission. So obviously, to tackle these very complicated tasks, that rover is going to be a very complex design. And it has, as I mentioned, a very similar body to Curiosity, but inside of it has a whole lot of new scientific instruments that's going to help it do those tasks I mentioned on the previous slide. So I'll just point out a couple. So here on the right side, we have Sherlock and Pixel. So those are incorporated into that arm that's going to be collecting samples. And that can help us do that analysis right there on Mars. I also like to point out MOXIE. This is a really cool technology demonstration opportunity that we have where they're actually going to be trying to produce oxygen from the carbon dioxide atmosphere on Mars. So if we ever want to send humans to Mars, we have to have a way to be able to help them breathe. And so being able to produce oxygen is an important step in that process. So these are some pretty great scientific instruments that lots of people have been developing for many years to put onto Perseverance to send to Mars. And they're going to be doing a lot of work while there. One thing I also like to point out when I talk about Mars 2020 to people is that we're not just sending Perseverance. Maybe not all of you know this, but we're also sending a helicopter to Mars with it, and it's called Ingenuity. And this is not really going to help us do anything scientific on the mission. It's really just a technology demonstration. So this is something we've never done before. We've never flown with powered flight on another planet. So Ingenuity will be catching a ride with Perseverance to Mars so that we can see if that's even feasible. And that might help us in future missions. And one of the reasons it's really hard to design a helicopter for Mars is because the atmosphere is very low density. So it's less than 1% the density of Earth's atmosphere. So it has to work much harder to create lift, and that's what helps it get flight. So there's been a lot of design going into this helicopter over many years to help that happen. It has to be, for example, really light. That helicopter is only 4 pounds. It also has to spin the blades very quickly. I think it's something like 10 times faster than what the blades would spin on Earth, just to be able to generate lift for that light helicopter. So it's going to be catching a ride and doing some test flights, and I'm really excited to see if it's successful. So that could be a big game changer for future missions to Mars. So these are kind of the areas what we're looking forward to when the robot finally gets to Mars. But one thing we haven't talked about yet is how it gets there. And this is the kind of stuff that I work on at Ames, and this is where Ames contributes a lot, is to the actual technologies that enable us to make these missions happen. How do we actually get there? And that all started yesterday with the launch. As I mentioned, we had a successful launch yesterday, and it took off without any problems. And I heard Chabot had a viewing party, so I hope a few of you were able to attend and check out that launch. So we used the Atlas rocket on this launch, and it's a pretty impressive rocket. It's more than 1 million pounds in weight, and it's really tall, 191 feet. And I think it's helpful to really see what the perspective of the rover is compared to that. So in this top, inside the payload fairing at the top of the rocket, you can see the spacecraft is there just at the bottom. You can see it's a really small part of just the tip of that rocket. And of course, we have Perseverance tucked inside of that spacecraft. And really, that's just a small little part of this really tall rocket. And we just have to bring a whole lot of fuel with us on that rocket just to get us out of Earth's gravity, right? So we need a whole lot of force to be able to pull out of Earth's gravity and get the spacecraft on the way to Mars. So it's really an impressive, I mean, rockets are things we've been doing for a long time, but I still think an impressive feat to be able to send something all the way to Mars like that. All right, so once it's up into Earth orbit, it's actually kind of a two-stage process. We launch the spacecraft to the orbit, and then from orbit, we launch it off to Mars. So the picture on the left here shows you what it looks like, an illustration of that spacecraft getting launched, and all of that rocket parts just get left behind. And so most of that 7-month journey looked like that picture on the right. So we just have a cruise stage, and that spacecraft just kind of basically is on cruise control all the way to Mars. And that journey will take about 7 months. So come February, we'll get to see what Perseverance has in store for us. All right, so the really exciting part, this is the part that I work on, but the most exciting part of the journey to Mars is really once we get to Mars. And that process is called entry, descent, and landing. All right, so that starts from when the spacecraft first enters into Earth's atmosphere, and it goes all the way until we can finally safely land it on the surface of Mars. And there are really a whole lot of technologies to go into this process. It's a very complicated design. I'm still amazed at how they can make this happen. And this whole process, which is slowing down the rocket from many thousands of miles per hour to land safely on the surface of Mars, is just a 7-minute process. And in fact, I think this is really cool. I would rather show you a video to show you all the moving parts. And they put out a video, Jet Propulsion Laboratory put out a video for Curiosity. And as I mentioned, that mission is very similar to this current mission. So I'm going to play that video for you.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought. But it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the skycrane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Great. So I just think that's a really great video to show the whole process all the way from entry to landing. And it really describes all of the technologies that go into this. And it's really a huge team of engineers that have to make all this work. It's just really quite impressive. And so what I want to talk a little bit more about is the first part of that, and that's the entry part. And that's what I work on at Ames. And Ames really does a whole lot of work on many of those pieces, but the part that I'm most involved in is with the entry system itself. So here in this case, when we first get to Mars, the spacecraft is traveling very fast and it hits the atmosphere at Mars and it starts to create a whole lot of heat from the atmospheric drag. There's a whole lot of aerodynamic heating that's going on, and that creates basically this glowing light that starts heating up that spacecraft. So we have to do something to keep that spacecraft and that rover inside safe before it can get to the rest of those technologies. And that's where the heat shield comes in. So this heat shield is this kind of orange, yellowish colored thing on the front of the spacecraft, and that's what helps protect it from all that heat. And there are a couple of components that go into the heat shield. One is the shape. You'll notice that it's a blunt body. Now, this is something that was actually invented at Ames, this idea that we could use a blunt body to help slow us down and help keep us safe. And that blunt body helps direct all of the hot air away from the spacecraft. If we had something that was a sharper point, all that heat would just go right into the spacecraft. So that blunt body is an important point to make that heat shield work. Another component of it, though, is the materials. So we need materials that can really withstand these extreme conditions and keep the inside of the spacecraft safe. So we use in missions like this what are called ablative materials for the heat shield designs. And in particular for this mission, for Perseverance as well as for Curiosity, we use a material that we designed at Ames called phenolic impregnated carbon ablator, or PICA for short. So this is what this heat shield looks like on the left. You can see it's yellow. And the reason it's yellow is because it's impregnated with a phenolic resin, and that gives it that yellow hue. But on the inside, the carbon part of it is this microstructure, these little tiny carbon fibers that make up this network that holds, it's kind of the structural component of that material. So all of those holes between those fibers get filled with this infused resin, and that's what keeps the structure safe. So we have on the left, you can see there are multiple yellow tiles that go onto that heat shield, and those tiles get bonded directly to the structure underneath. And there's a process that goes on that helps keep that safe during the high heating temperatures. So here's just a quick schematic of what that looks like. So beforehand, we have this nice pristine tile. And what happens once we start to see those high temperatures is that we start to decompose that material. This is by design. So this is not a mistake. We have these materials and we've designed them to decompose at these temperatures and char, kind of like you would see wood in your fireplace starting to char. And all of that decomposition process actually takes out some of the energy that's associated with the entry process and pulls it away from the spacecraft. And it creates gases that come and get blown out of the heat shield. And that also creates this layer along the top of the heat shield that keeps all the hot air moving away. So this keeps the heat shield very safe on the inside. So it might be really hot at the front, but behind that structure, it's going to be nice and cool, keeping the structure safe and keeping the rover safe. So this is a really cool process. Again, so Pika, this material was designed at Ames, and we have several ablative materials, but this is the one that's on the Perseverance rover. So one thing we need to think about, though, and I don't think some people appreciate, is how do you think we might test these types of designs when we're going to another planet? So we can't just make a heat shield and send it to Mars and see how it works, right? We got to be pretty confident when we send that heat shield the first time that it's going to work right. So we have to get creative at NASA about how we can do that testing. And we have a lot of cool facilities that help us do that. And the one that we have at Ames is called the Arc Jet Complex. So this is basically a big plasma arc gun. It just shoots really hot gases at a material sample, and it lets us see how a material might respond in an environment that's very similar to entry. So you can see this picture here as an example of a sample of Pika. You can see that yellow color, and it from right to left is moving this hot gas flow that kind of replicates that entry environment that you see on the right. And I actually have a video of this. So this is it's not a Pika sample, but I wanted to show you a process, what that testing looks like.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Arc on.
Okay, we're at conditions. Setting up overhead. Overhead's going in 5, 4, 3, 2, 1. Seconds. 40 seconds. 60 seconds. 80 seconds.
All right, so that's what testing in the ArcJet looks like. And so that's one way that we can quickly design materials and give them a test right here on Earth so that we know when we send it to Mars, it's going to work just right. I mean, we don't do that alone. So that testing can get very expensive. It's not practical to do a lot of design with just the ArcJet. So we also do a lot of modeling. And this is one of the things I work on at Ames is modeling of heat shield materials. And that modeling can take place on different length scales. But one of the things we do is actually model the whole heat shield, like this simulation that I'm showing here. So in this case, we want to understand how the material, in this case, Pika, is going to respond given a certain entry condition. So we can calculate the trajectory to Mars and we can know exactly what angle it's going to enter at. And from that, we can determine how hot the air is going to be. And then using some mathematical equations, we can understand how the heat's going to transfer in that material. And we can start to see where it's going to get hot, where it's going to get the hottest, how hot it's going to get in those regions. And we can actually incorporate also equations to understand that ablation process. So how far is that material going to recede down? How much of it's going to decompose and char? How much are we going to lose? right? So we need to make sure that we make that thick enough so that everything inside stays safe. So these simulations are a great way that we can help understand what our heat shield needs to look like when we send it to Mars. All right, so that was some of the technologies and materials that we use for Mars 2020. I also wanted to give you some sense of some of the future stuff that's coming up. And I kind of alluded to this already, and this is Mars sample return. So we have an idea for a new mission coming up in the near future where we can go collect those samples, all starting with the Perseverance rover. So it's going to collect those samples and bring them to the surface of Mars so that we can go pick them up at another time and bring them home. And that's going to be a very complicated process. And again, I have a nice video that'll show you that. So let me pull that up.
Hi, I'm Raquel Villanueva here at NASA's Jet Propulsion Laboratory. Now, it has been a dream of scientists for generations to bring back samples from the surface of Mars. Now, right now, the Mars 2020 rover mission is laying the groundwork for that to happen. And that's why I'm in the In Situ Instrument Laboratory with Jessica Samuels, and she's here to tell us what's going on here.
Well, we use this facility to develop and design our hardware and software systems for our Mars mission.
And how does the sampling system work?
So we have a drill on the end of our robotic arm, and as we are drilling the surface of Mars, we will be collecting pieces of Mars into the sample tube at that time. We'll then transfer that sample tube into the inside of the rover and then seal it for storage as we continue to explore the surface. After we've collected a diverse set of samples, we will drop them off onto the surface and then have them there for our future sample return mission to continue.
Well, I know you have some tests to keep doing, and I'm actually going to go check out the next phase at a different lab. We're in a testing lab affectionately known as the Sandbox, and I'm here with Austin Nicholas. Now, can you explain how we are going to bring back samples from Mars?
So starting from after 2020 has deposited tubes on the surface, there are 2 more missions to go in bringing the tubes back to Earth. The first is a lander mission. It carries 3 major elements: a sample fetch rover and a sample transfer arm that lets you transfer the samples from the fetch rover into the rocket, and a Mars ascent vehicle, which is a rocket that brings the samples from Mars into space. Meanwhile, the orbiter has also launched from Earth in 2026 and is making its way towards Mars, and it'll be in position by the time the rocket's fully loaded. The orbiter will then go to the sample container that the rocket's put into space and then capture it, ultimately bringing them to Earth in 2031.
That sounds complicated.
It is complicated, but fortunately we're not doing it alone. So we have a great partnership with the European Space Agency, and they're providing some major pieces of this mission. Within NASA, we've actually got a number of centers working on all of the different pieces. So we're partnering with Marshall Space Flight Center for the Mars Ascent Vehicle, Langley and Ames for the Earth Entry Vehicle, Glenn for the Sample Fetch Rover wheels, and we're partnering with Goddard for the orbiter payload. And so there's really it's a whole NASA effort to get Mars sample return done.
Sounds like there is a lot of work to be done, but this all kicks off with the launch of Mars 2020 this summer in Cape Canaveral, Florida. And there's lots of excitement here as we get ready to make history.
All right. So that's a little bit about the Mars sample return mission. And this is something that we would like to do. It's proposed so far. It's not selected as a mission yet, but this is something we would like to do in the near future. And as you might imagine, there are some new complications about bringing samples home. And so that's required a little bit of new material development. And there are 2 specific materials I want to tell you a little bit more about. And the first you saw a little bit about in the movie, and that's these new rover tires that have been developed. So what we've noticed on previous missions is that the really harsh conditions on the Mars terrain, that might be the lots of dust, the heat, and the temperature swings high to low, the rocks that the rover has to go over, it created a lot of damage in the Curiosity tires. So we wanted to do something to fix that. And that's something that they've been working on for many years, particularly out of Glenn Research Center. And they came up with this new design for a tire that's similar to a spring tire that's usually done with simple metals, but they incorporated a new component using what are called shape memory alloys. So the simple spring tire design is basically an airless tire. You can see the picture on the left. But typically when you use a normal metal for this, what will happen when you roll over a big rock like that is you'll see permanent deformation in the tire. And maybe you've played with springs before. If you stretch it too far, it won't go back, right? So that's perfect. It's now permanently deformed. So in order to prevent that from happening, because we can't have tires going bad on Mars, it's not like we can just go and change them. They thought about how we can incorporate these new shape memory alloys into the tire to prevent that deformation. And those tires are actually much more durable than the original tire design. And it uses this effect that happens at the atomic scale. And I've demonstrated here with this schematic here. And it's actually a transformation of the atomic structure between two different crystal structures. So as it rolls over that rock, those atoms will shift into a new configuration to allow for that change in the structure of the tire. And then when it is finished rolling over, it go back to the original structure. And that's what gives it that shape memory effect. So it remembers what its structure was before. That way, any deformations are able to return back to the normal tire shape. So this is a really cool material, and they're going to be testing this out, hopefully on the Mars sample return mission. And I think it's going to be used in a lot of missions moving forward. All right, so the second material I wanted to tell you about is relating to the entry system. So I told you a little bit about Pika and how we used that for the Perseverance mission and for the Curiosity mission. But we've been also working on some new heat shield materials at Ames, and one of them we recently developed is a woven composite. So very similar to Pika, it's still impregnated with that resin, that yellow color resin that you saw in Pika, and that helps take away some of that heat when it decomposes. But now that carbon structure that was before a random network is now a woven fabric, kind of like your clothing. And so this new material that we developed at Ames is called HEAT. You can see the name there on the bottom. And this is something that we're thinking about for this new mission, because obviously when we're bringing samples home from Mars, we're going to have very strict requirements to make sure that there are no risks for contamination. And that is not just contamination to Earth, but we also don't want to have any risk to contaminate those samples that we're bringing home. If we spend all that energy to bring those samples home, we need to make sure that we can land them safely on the surface of Earth without any damage to the samples or any contamination risk to us. So this was a new material that was designed that'll let us do some missions that Pika wasn't designed for. And so this is going to be kind of the new frontier of heat shields for new missions in the future of NASA. All right, so now I want to step a little bit further forward. So we talked about the Mars 2020 mission that's going on now. We talked about Mars sample return, which is going to be in the near future. You are probably also thinking, what about sending humans to Mars? And obviously that's a very complicated process. We're far away from that. We have a lot of technologies that we need to develop. But that's something that we're starting to work on through the Artemis program. And maybe some of you have heard about this, but this is a new program that we've decided to spend more effort returning to the moon so that we can help prepare technologies that would get us safely to Mars. So this is kind of kicking off recently. We have a crewed mission that we would like to do in 2022 on the new Orion spacecraft that you can see on the left side of the screen, followed by sending back humans to the moon in 2024. And that's going to be followed with many missions to help us develop new surface technologies, maybe to help us create resources from either the moon or Mars, or to help us build surface habitats. We're also going to be developing a lunar gateway that can act as a staging station between the moon, between those moon missions. So as you might imagine, there are now a whole bunch of new technologies that are required to think about sending humans to Mars. And we're going to test some of these now. And obviously, as we start to test those, there are going to be new material constraints. And one of the technologies I want to talk to you about is an advanced propulsion technology. So the idea behind this is, how can we get to Mars in less time? So it doesn't matter if the robot is taking 7 months to get to Mars, but it's much safer for humans to get there faster. There's a lot of radiation exposure in space. So we would really like to reduce that time before we send humans to Mars. And a new technology called nuclear thermal propulsion is one of the opportunities that we have. So I'll play a quick video here that I'll show you a little bit what that's about.
First-generation nuclear thermal propulsion, or NTP, could enable both faster transit between the Earth and Mars and a series of advanced space missions. Nuclear thermal propulsion is powered by nuclear fission, which has been used on Earth for more than 70 years. How it works is conceptually simple. Energy from fission is used to heat hydrogen to about 4,400 degrees Fahrenheit. This hydrogen is then accelerated through a nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. Nuclear thermal propulsion was considered for use in the Apollo program, and significant development and ground testing was accomplished. Advances in technology since the 1960s may improve its affordability, viability, and acceptability. For example, it may be possible to fuel modern NTP systems with low-enriched uranium instead of highly enriched uranium. In addition, it may now be possible to ground test NTP systems at established, safe, self-contained rocket engine test facilities. For human Mars missions, the physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant. However, the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. That energy is used to get astronauts to Mars faster. NTP can take months off the trip compared to using traditional chemical systems, reducing risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also facilitate the development of fission surface power systems, enabling a power-rich environment at any exploration location. Abundant power could also be used for in-situ resource utilization, life support, communication, and other diverse applications. First-generation NTP systems are a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system.
All right. So as the video talked about, we did a little bit of testing on nuclear thermal propulsion back in the 60s. And actually one of the reasons that that program stopped was because they ran into a lot of issues with materials. And a big question here is, we have to have materials that can withstand very high temperatures and very corrosive environments in the reactor core of that nuclear rocket. So you can see this picture of a schematic of that rocket there on the left. And inside we have all these fuel core elements given by this hexagonal shape in the middle there. And those materials have to be exposed to super high temperatures and also to a hot flowing hydrogen fuel. And that temperature, hydrogen starts to eat away. There are a lot of chemical reactions that can happen with that material. And in the old testing, they noticed that there just weren't materials available that could stand up to that. So now that we're renewing our interest in nuclear thermal propulsion, a big push is in designing these new materials that can help make this technology a reality. And that's one of the things that I've been working on recently, and it's been getting a lot of interest at NASA again. And there are a few ways that we can test this on Earth. Again, we can't just send things up to space and test them out. So we have some new facilities that we can take advantage of. And one is at Marshall's, and it's called the Entries facility. And this lets us test at really high temperatures, and it actually lets us flow hot hydrogen over material so we can see how it responds. So bad materials are going to start to corrode or react with that hydrogen. And maybe, in fact, many metals are going to actually melt at that temperature. So we have to design new materials that can withstand that very bad environment. And one of the ways that we can speed up that process, it's very slow to do that, time consuming to do that just with experiments, trial and error over and over again with these very expensive facilities. One way we can speed that up is using modeling and simulation. So I mentioned way back at the beginning that we have a supercomputing facility at Ames, and that's one of the things I work on is the modeling and simulation aspects of understanding materials. And you can see the similarities between understanding heat shields and how they operate in high temperatures, and understanding materials for thermal rockets and how they operate in high temperatures. So we have a lot of capabilities at Ames that help us understand these material behaviors. And we can actually model the material all the way down to the atomic scale, considering every atom in the system. And that's what this video here on the right is showing you. It's actually a simulation of all the atoms. It's something like 4 million atoms inside of this box that is shown. And I'm just showing a slice of that. And you can see the grain structure of this metal. And we can start to see how that material is going to respond at the atomic structure when it's exposed to different types of environments, whether that's high temperatures or to extreme loads. And so we can start to understand the failure modes, how those materials might fail in these conditions. So right now we're working on coupling these two examples using both experiments and simulations to speed up that design process. And that's going to be an important point to make nuclear thermal rockets a reality. We're going to have to solve these material problems, and I think we'll come up with a solution soon. All right, so I hope I gave you a good flavor about some of the material problems that we work on at NASA. Obviously, there's a whole lot that goes on at NASA, and I can't talk about all of it. And I tried to condense as much technology related to Mars exploration as I could. But I wanted to point out a few resources that you might be interested in looking at on your own time. So I have here a couple of links, and I'll leave this up for a few minutes. So we have a whole bunch of NASA at home activities that you can check out. There's stuff that's great for the younger audience as well as older audiences. And we have the NASA STEM at home, for example, that's got a lot of activities for different school age groups. The STEM demonstrations are demonstrations done on the ISS. Those are a lot of fun to see. If you want to take some fun photos in the Mars environment, I'd encourage you to check out the Mars photo booth. Or if you'd rather have a printed poster, you can actually download this poster like the one I have behind me. So those are all on the NASA website. We actually have a few apps as well. JPL made a few apps related to the Mars missions and other missions that they've done. So you can look up the Selfies app and the Spacecraft app on any of your devices. And then lastly, I wanted to mention some of the podcasts and live show that NASA has. So NASA actually has many podcasts. I'd encourage you to go check them out. In fact, Houston, we have a podcast. That's one of our podcasts. They recently did an episode on Perseverance. So that was a good one to listen to, and you could still check that out anytime. And then at Ames, we have a live show called NASA in Silicon Valley Live. And obviously we're not doing live shows right now, but you can go watch all the archived old shows. There's actually one on thermal protection materials and testing in the arc jets. So I would encourage you to check those out. All right, so I think at this point we can take some questions.
Thank you, Dr. Abbott. That was a really wonderful insight into Mars 2020 and all that goes into it. If you have some questions for Dr. Abbott, feel free to please put them in the chat, and we will wait to answer some of your questions live. We can go on for about probably a couple more, 10 to 15 more minutes. I have one. Is it possible to create drinking water on Mars for future astronauts?
Yeah, so finding out ways to be creative about getting resources on Mars is definitely one of the key challenges to getting humans there. So I mentioned that MOXIE technology that we have on Perseverance that's going to be trying to create oxygen from the carbon dioxide. Definitely creating water is another thing that we're looking at. And one of the things we like to do under the Artemis program is really test out these types of surface technologies on the moon and use that as a learning ground before going to Mars. So that's definitely a high priority item, and using those resources from either the moon or from Mars are going to be critical to having these long duration missions.
Great, thank you. One question that came in earlier was about the rotor blade design or the RPM they were wondering if it had to be different for Mars's atmosphere.
Yeah, so as I mentioned, one of the difficulties in the Mars atmosphere is actually it's very thin. So I mentioned it's less than 1% the density of Earth. And what that means is it's much harder to create lift in the robot or in the helicopter. So in that case, those blades have to spin much, much, much faster. So if we need to get lift on Mars, in order to be able to push down enough air to give us that lift or enough atmosphere to give us that lift, they do have to spin a lot faster. And so one of the things that we've been doing at NASA is running simulations on different designs, both real life simulations in vacuum chambers, as well as simulations on computers to help us fine tune that design of that rotor blade design, what shape it needs to be to give us the best possible lift. So they've settled on that design and they've had some good tests. I think you can actually watch some videos online of the tests that they did with Ingenuity, and I'm looking forward to see if it works on Mars.
How is this different from the Viking mission in 1976?
Well, so the Viking mission was a long time ago. We've done a whole lot of new technology development since. Every time we send a new rover to Mars, it's got a little bit more in terms of bells and whistles than the last mission. And one of the things to also think about is when we have a rover or a lander on Mars, it's usually not going very far. So even our last rover, they only travel a few miles in their full lifetime. I think we've traveled less than 50 miles or maybe about 50 miles total on the whole surface of Mars. So even if we just kept sending the same rover to different parts on Mars, there's new stuff we might learn just because there's going to be diversity across the planet. Just like on Earth, we have areas that are very different. So even without new technologies, each mission is going to be an opportunity to learn more. But as I mentioned, we've developed a whole lot of new technologies that give us more capabilities in terms of how light everything can be, so we can jam pack more instruments on there, the precision with which we can measure things. So all of those things help us get more accurate measurements and more data to collect from Mars.
Another question that we had was, what makes the Mars sky red?
What makes the what?
The Mars sky red.
So it has to do with the minerals inside of in the Mars environment and the carbon dioxide atmosphere. That's a great question. I'm not too familiar on the exact specifics, but I imagine you can find that out. If you go to mars.nasa.gov, there's a whole lot of information about Mars. So that would be where I would start.
What is the life expectancy of the Perseverance, and can parts of it be used for future missions?
Yeah, great question. Yeah, so reuse of a rover would sure be nice. Right now, it's not very practical to reuse parts of the rover just because we're usually not sending rovers to the same place. And typically, there is a duration, an expected life duration for the mission. I think for Perseverance, it's 1 Martian year, so I think that's about 2 Earth years. But typically, if you remember my first slide on the timeline of the Mars missions, our rovers have had a history of running far past what they've been designed to do. So we've only planned to collect data for a year, and that's really our primary mission. But oftentimes they're built to last, and so they'll keep collecting data for a long time. So Curiosity has been going for a while, and we've just been able to collect as much as we can from every rover for even more than 10 years. So I wouldn't be surprised if we see Perseverance going for many years to come.
It's exciting. Here's another question. What powers the helicopter, and how long can it fly?
Yeah, so helicopter, as I mentioned, is just a technology demonstration. So we're not shooting for really long flights. It's going to be taking just quick hops, I think on the order of minutes. I'm not sure if it's 5 minutes or 30 minutes, but they're very short flights. It's, I think, powered by solar panels to help it fly. And just because it has to do these really short hops, it doesn't need a whole lot of power. And I also mentioned it's really light. So that was a critical component of the helicopter, to make it really light to give it the best chance of success. So it's not designed for any long missions. Certainly in the future, if we wanted to incorporate a helicopter that would maybe scope out the territory for our rovers in the future, we would need to improve upon that design. But we're just trying to see if we can do it at all. And I think that in itself will be a great feat.
This one is about your personal career. What made you decide to study science, and what was your education path?
Yeah, so I think you could probably ask a lot of people at NASA, and they would never expect to end up at NASA. I certainly, even a few years ago, I've been here for 3.5 years, maybe even 5 years ago, I never would have expected to be here. I think for most scientists, it's kind of fate. You just end up at place after place, and you're in your current position, and something comes up and you go on to the next, and you have to be open to those opportunities. And that's how I got here. I've always been fond of science. I was into mathematics as a kid, into programming and physics. So that's what I started with in my undergraduate degree, with math and physics. But I really liked the application side of it. And that's what made me veer into material science. So material science is kind of a special science in that it's very interdisciplinary. You really need to bring in backgrounds from chemistry and from physics, chemical engineering, all sorts of mechanical engineering, all sorts of information goes into understanding and designing materials. So I was able to take that mathematics and physics background and apply it to these applications and materials. And one thing led to the next. So I was at Sandia National Labs for a little bit in Albuquerque, New Mexico, before I ended up here. And I've just had a chance to work on some pretty cool materials problems in my career so far.
That's awesome. How big will the return sample rover be?
I don't know if the design for the return vehicle has been finalized yet. So I mentioned that's just a campaign, so it's just a pitched mission at the moment. It's not an official mission, so there are no finalized designs. I think they're playing around with a few ideas still on that, so I can't give you any definite answer. But it's got to be big enough to go around and collect. One of the difficulties in the Mars environment is being on that harsh terrain, so you have to worry about how big that robot is to make sure it's not going to tip over or get blown over or anything like that. So. It'll be sizable, I imagine, but probably not as big as Perseverance.
We have a few more questions that have come in. What materials do you expect to find on Mars?
Well, we have some ideas about what's on Mars already. So one of the things that we can do even from orbit is understand some of the light signatures that are coming off of Mars, and that can give us some sense in the minerals and whatnot are on Mars. So there's a whole lot of information. Again, if you go to mars.nasa.gov, you can learn a lot about the types of information that we've collected from different missions in the past. And that's going to be critical. We talked about this earlier, using resources from Mars. So one thing we can determine in not just understanding the science of how the planet formed, but also what resources might be there that we can use in future missions.
Someone is asking, what about Kepler 452b? That's the whole question. So
I'm sorry, say that again?
The question was, what about Kepler 452b?
Yeah, I mean, I don't know what about, is there something more specific to ask?
Sorry.
No.
We can move on. Do you know the reason behind using a helicopter rather than a drone model?
A drone?
Mm-hmm.
So it is an automated helicopter. I mean, it's similar to a drone. I think that it's just a question of what's the lightest you can make it and how you can take advantage of. I know there was a design using 2 blades because you have to be able to prevent the helicopter from spinning on itself. So I know they tested lots of designs, and I wouldn't be surprised if there are more drone-like designs out there as well. But this is the one they thought they had the best chance with.
That is great. We probably will have time for one more question. This last one says, could you repeat the missions that NASA needs to send back the samples?
Yeah, so it's actually a very complicated process. So right now we have Perseverance on the way to Mars. So that's the first part of the mission, even though it's a separate mission. It's what's laying the groundwork for Mars sample return. In the future, I think they're aiming for 2026 right now. They're going to be 2 new missions. One's going to be sending the new rover and lander to Mars. So that rover is going to go to Mars and pick up those samples, and it's going to bring those samples to a lander, and that lander is going to then send the samples up into orbit. So that's the first mission. The second mission is an orbiter that's going to be sent at the same time, and it'll be waiting around Mars to collect those samples from the lander on the surface of Mars. So the samples will go from the Perseverance tubes to the new rover to the lander up to the orbiter, and then that orbiter will send it back to Earth in an Earth entry vehicle, and that we're anticipating to be around, I think, 2031. So it's a very complicated process. We're still designing all the elements for that, but I think it's going to be a very exciting mission.
This is all so exciting. Thank you, Dr. Abbott, so much for taking the time to be with us today. And thank you for such an incredible insight on the Mars 2020 missions. And I'm looking forward to February when we can watch this land on Mars. It'll be very exciting. And thank you all so much for tuning in. We have programming every Friday evening at 8 p.m. And also on Saturday evenings at 9:30, we have our virtual live telescope viewings with our resident astronomers. And you can visit our website at chabospace.org and click on the event button to see a complete listing of all of our upcoming virtual programs. While we work towards a grand reopening, we appreciate everyone's time and support as we find new ways to learn together. These events are fueled by you, our community, and special thanks to our members, donors, and partners for helping us bring science to life to everyone at home. Right now, STEM education is more important than ever, and we need your help to keep these virtual STEM programs free and accessible for everyone. You can make a difference by donating here on Facebook or at chabospace.org. Thank you all so much. Thank you again, Dr. Abbott, for this wonderful talk and insight on the Perseverance Mars 2020 mission. And thank you all, and we'll see you next time.
Thank you.